This lesson builds on working with formulas with permutations and combinations lesson 1, and it builds now to where we start solving using the formula for certain values of n within the formulas themselves. So in order to work on this lesson, we need to have the handout, which is lesson 4 from puremath30.com. So you can either get it from the teacher right now, or you can download it at puremath30.com. And specifically, we're jumping in here now to where we're going to be working with the formulas themselves to solve for certain values of n. So these are different from the ones we did in the previous lesson. Now, each of these are no longer expressions, they're equations. They have an equal sign, which means there is a value or values of n that could work. So we're just going to start looking at these. It says solve for n in the following equation: n plus 2 factorial over n plus 1 factorial equals 8, and saying what is the value of n that would make this true. So to start doing it, again, we look at the numerator and the denominator, decide which is bigger, n plus 2 or n plus 1. Well, n plus 2 is definitely the larger of the two factorial statements. So n plus 2 factorial, we start counting down to n plus 1 factorial. That matches the bottom. This whole thing equals 8, which tells me n plus 1 factorial and n plus 1 factorial divide out to 1. So this simplifies to n plus 2 equals 8. A simple solving here, subtract 2 from both sides, n equals 6. So in this case, 6 is our answer. And you can go in and verify it, left side equaling the right side of that equation. But in any case, n equals 6 in example 1. Example 2 gets a little bit more complex. We have an n on both sides of the equation now, but the same sort of idea follows through. Look at your numerator and the denominator, decide which factorial statement is in fact larger, count down till you reach the other one, simplify them, and then we start working. So in this example, n plus 1 on the top is definitely larger than the n minus 1 factorial on the bottom. So if we start counting down, n plus 1, after that is n plus 0, or just n, then we reach n minus 1 factorial. Remembering this whole thing still equals 10n, we should be able to identify that these two things would divide out to 1. So my statement would be left with n plus 1 times n equals 10n. Now we have to solve this equation for n. First thing I do is distribute this n on the left-hand side. I get n squared plus n equals 10n. I'd bring all my n's to one side of the equation, so I'd get n squared. I'm going to subtract this 10n from the other side, and I get negative 9n equals 0. So now we have to solve this. This is where factoring is going to come into play. I'm going to move this up here a bit. We'll continue to solve. Here's what I have. N squared minus 9n equals 0. These two terms have a common factor of n, so I'm going to factor that out. N and n minus 9 equals 0. Now this comes back to our grade 10 skills where we set both factors equal to 0. So first off, n might equal 0, and this guy, n minus 9 equals 0, which I solve, n equals 9. Now on first glance, it would look that this actually has two solutions. However, n is not allowed to equal 0 in this case, because if it did, if I look back in the original equation right here, I'd be saying 0 minus 1 factorial, which would give me a negative 1 factorial. And we talked earlier that we can't have factorials of negative numbers. So this right here is not a solution. n equals 9 is the only solution in this example. Example 3 now is a little bit different looking. We don't have a fraction to begin with. We have n plus 3 equals 20 times n plus 1 factorial. What we want to do in this case is to bring the factorials to one side. Now this is a multiplication of n plus 1, so if I move it to the other side, I'm going to get n plus 3 factorial all over n plus 1 factorial, and this equals 20. Now this resembles the type of examples we've worked with before. The numerator in this case is the larger factorial, so we're going to start counting that down, n plus 3, n plus 2, and I can stop at n plus 1 factorial because that's all over n plus 1 factorial. This still equals 20. Looking closely, we know the n plus 1 factorials divide out to give us 1. So this simplifies to n plus 3 times n plus 2, all equaling 20. Now we have to FOIL or multiply these two binomials together, which gives me n squared plus 5n plus 6 equals 20. Bring the 20 over to make this statement equal 0. So we're actually going to have, and I'll move this down here a bit, n squared plus 5n minus 14 equals 0. Now we have to factor this quadratic. We need two things that multiply to negative 14, but add to a positive 5. That turns out to be n plus 7, n minus 2 equals 0. This gives me a solution of n equals negative 7. This gives me a solution of n equals 2. And again, for the same reasons as the last guy, I can't put a negative 7 into the original equation and have a negative factorial. Therefore, this root is non-existent, and the only solution that I'm left with here is n equals 2 for the final answer. So let's look up now at example 4, a little bit different. And this guy doesn't give us an equation to start with at all, so we have to go back to remember that NPR is actually n factorial over n minus r factorial and put in the information we need. So from here, I could say in that equation, that's n factorial over n minus 2 factorial, all equaling 56. Now the question resembles what we know. The top part is larger, so I'm going to count that down. N times n minus 1 times n minus 2 factorial, all over n minus 2 factorial equals 56. These will cancel. I'm just left on the top here with n times n minus 1, so I can simplify that to n squared minus n equals 56. Just like the last example, I'm going to bring everything over to make a quadratic equaling 0. So I got n squared minus n minus 56 equals 0. Getting a little crunch for space here, but I'll move the work up to here. I need to factor that quadratic, and if I factor that quadratic, we can see that it turns out to be n minus 8 and n plus 7 equals 0. That is the factors to n squared minus n minus 56. This gives me a solution of positive 8. This gives me a solution of negative 7, which you can already see is an extraneous solution. So the only answer in this case is n minus 8. Sorry, n equals 8. The last question down here, example 5, we'll look at, deals with combinations. And we'll remind you that a combination, the formula for a combination, NCR, is n factorial over r factorial times n minus r factorial. Again, that's on your formula sheet. So all we're going to do is put these into our equation. So we have to deal with the top and bottom separately. So the top, 400, choose 300. If we look at this equation over here, that means it's going to be 400 factorial over the r, which is 300 factorial, times those two things subtracted, which is 100 factorial. The 100 comes from 400 minus 300. And the bottom, if we put that into the formula, is going to be 400 factorial divided by, and we're looking at this part now, the r, which is 100 factorial, times those two subtracted, which is 300 factorial. Now some people see something right away. They're realizing that the numerator of this compound fraction is exactly the same as the denominator. So they know if I divide these, the whole answer should be equal to 1. If you don't see that, we could take it a step further and remember saying, well, to divide fractions, the numerator stays the same, and we multiply by the reciprocal of the other one. And when we start doing this, a lot of people understand now that the 400s are the same, the 100 factorials are the same, the 300 factorials are the same, and when everything divides out, this whole answer equals 1. So working with these solutions, you really have to check to make sure that all of your solutions are actually viable answers and doesn't lead to negative factorials. So right now, go through, work these questions. You have the answers provided as well on the next page, actually the solutions. So work through, get those done, and we'll continue the lesson.